the overall statistic for the table is determined by summing up all those cell-by-cell calculations. All right, now so we add all those cell-by-cell calculations up. We add them up and we get a value, an aggregated summed value of 15.2 for all those numbers. So what? The null hypothesis says it should have been 0, give or take random sampling error. How do we figure out the amount of random sampling error that's contained in that 15.2? That's a complication in chi-square that you don't run into when you're doing normal estimation. Let's talk about it. The size of the chi-square statistic that is needed to, and I'll just say beat the null hypothesis, depends on the degrees of freedom in a table, or the number of rows and columns of a table. The more numbers, the more rows and columns that a table has, the greater the degrees of freedom, and the calculated value of chi-square that you need to beat the null hypothesis is higher. Degrees of freedom for any table is equal to the number of rows minus 1 times the number of columns minus 1. So in our example, we have 3 rows, 3 minus 1 is 2. We have 2 columns, 2 minus 1 is 1, yields 2 degrees of freedom. The number of degrees of freedom determines the shape of the distribution. Unlike the normal distribution, which always assumes the same shape, chi-square, the chi-square distribution depends on the structure of the table, the number of degrees of freedom. I found this interactive chi-square applet that has been provided by Professor Matt Bogner at University of Iowa. We thank you, Professor Bogner, for this. Open this up. Now, for example, our table has 2 degrees of freedom. Let's just put 2 in there. Here's what the distribution looks like for 2 degrees of freedom. It's an odd-looking distribution. As you go out here, you wonder at what point these are calculated values of chi-square along the base here. How big does the calculated value have to be to get out to where there's only 5% of the curve remaining? So what's called a critical value, the value that you have to beat in order to reject the null hypothesis, depends on how many degrees of freedom you have. Okay. Let's put 5 in here just to show you how this distribution changes. Now the chi-square distribution looks different, and you can see the shape. Now the 0.05 region is going to be out here somewhere. Looks like about beyond 11 would be about 5% of the curve. And again, let's put 10 in here. I mean, now chi-square is starting to look almost symmetrical, and at certain levels of degrees of freedom it does approach a normal distribution. The current point, though, is as we go out into the frontier, notice these calculated values of chi-square now are much higher. That for tables that have a lot of rows and columns, it becomes more likely that random probabilities are going to produce departures from expectations, and so we have to accord the null hypothesis more and more territory. It looks like we have to go out here almost to 18 or 20 to get into the region of the curve that is in the 0.05 level of significance. In fact, let's go back to 2 degrees of freedom, and let me illustrate something here. I'm going to put a number in here. That says chi, or it says x, but it stands for a calculated value of chi-square. I'm going to type 5.991, and I'm going to hit enter. And it says the probability above that value of 5.991 is 0.05. Here's the value I put in of 5.991, and this is in the pink area here. This is the 0.05 region of the curve. Let me put 5 in here again, and I'm going to put in the value 11.07, and again it says 0.05. So whereas before we had to get a calculated value of chi-square that was greater than 5.99, now when the table is larger, has 5 degrees of freedom, we have to be all the way out here at about 11.07 to return 0.05 to the right. One more example. I'll put in 10. critical value here is 18.307. Hit enter. And again, if you get 0.05 all the way out here. So for a table that's very large with a lot of rows and columns, and for which random probability, random chance is going to create a lot of noise in the table, you have to have a calculated value of chi-squared that is greater than 18.307 in order to defeat the null hypothesis. These numbers that I've been practicing with here, the first one was 5.991, the second example was 11.07, that was for 5 degrees of freedom, and the current one, which is 18.307 for 10 degrees of freedom. These are what are called critical values. A critical value is a value that defines the boundary between the null hypothesis' territory and the rejection of the null hypothesis. In this example, and let's go back to the one that we're using here, this is what the curve looks like here. For this example, if we have a calculated value of chi-squared that exceeds 5.991, that's the critical value, we would reject the null hypothesis. In this case, we're going to reject it because our calculated value for our table was 15.2. So the critical value approach is much like the 95% CI approach. It gives you a number, of a level of confidence, a number that defines the confidence that you have in rejecting or not rejecting the null hypothesis. In our example, the null hypothesis owns all the territory between a calculated value of 0 all the way out to 5.991. We own, the alternative hypothesis owns all the territory beyond that out here in this region of the curve. Also, I can demonstrate here. Let's put in the actual value that we calculate. We can get a p-value. The computer analysis that you are probably going to be doing will return a p-value, probability value, or a sig value. I'll put in 15.2, and here this applet returned 0.0005. Under the assumption that the null hypothesis is correct, we would obtain that the observed data that we got in that table about gender and diplomacy versus force looks like 5 times out of 10,000 by chance reject the null hypothesis.